The topic is continuous and discontinuous functions. And the examples are piecewise functions. So example 2, in the previous example we had an example of a function that's discontinuous at x equal 1 because the limit does not exist. So therefore it's also not continuous on its domain because 1 was on its domain. Now this example, so let's do this example. So first we need to check if we need to know if f is continuous at x equal 1. In other words, we need to check if f of 1 is defined. So let's check if f of 1 is defined. F of 1 is equal, since x, so we need to use this function minus 3x plus 6 because x equal 1 is included there. X is bigger or equal than 1. So plug it in. So minus 3 times 1 plus 6, minus 3 plus 6, which is 3. So it is defined because it's equal to number. Now we need to check 2. 2 says we need to know if a limit exists. So how do we know if it exists? We need to check the right and left limit. So limit of f of x as x approach 1 from the right side is equal limit. So we're approaching x from the right side of 1, then we need to use minus 3x plus 6. So this is a limit of minus 3x plus 6 as x approach 1 from the right side. Now this is easy, just plug it in. Minus 3 times 1 plus 6, which is 3. Now we need to do a limit of the function as x approach 1 from the left side. Now since we're approaching 1 from the left side, we need to use this function x plus 2 because x is strictly less than 1. So this is the limit of x plus 2 as x approach 1 from the left side. Now just plug it in, it's just polynomial. 1 plus 2 is equal to 3. Since the right and left limit are 3, therefore we can say the limit of f of x as x approach 1 is just 3. So the second condition is met. Now all we need to do is check 3. 3 said check if the limit and f of 1 are equal. And of course it is. So limit of f of x as x approach 1, it is equal f of 1. Why? Because this is 3 and this is 3. So therefore we can say f is continuous at x equal 1. Now next question is f continuous on its domain. Since the domain, just by looking at that, the domain is, first of all, the domain is negative infinity to infinity. So we always do this union that. So it's negative infinity to infinity. We know that by definition, here's the definition, polynomials are functions that are continuous on their domain. So for x smaller than 1 is continuous, for x bigger or equal than 1 is continuous. The only thing we needed to check is where the break happens, in other words x equal 1, but we already check it here. F is continuous at x equal 1, so therefore we can say f is continuous on its domain. Let's just graph it so you can see how it looks like. So y equal, so on the left of 1 we need to graph y equal x plus 2. So how do we graph that? That's a line. All we need is 2 points. So let's pick an easy one. When x is equal 0, we know y equal 2. So here's 1 point. When x equal 1, we're not supposed to use x equal 1, but we're going to use it, but we're not going to plot the point. We're just going to do circle that. When x equal 1, y equal what? 1 plus 2 is 3. So we're going to go here, 1, 3, but we're just going to use a circle because that point cannot be on the domain, and then draw our line. Right? Now, on the right of x equal 1, we need to graph y equal minus 3x plus 6. So again, we're going to use 2 points. We use x equal 1. When x equal 1, if we plug it in, y will be minus 3 times 1 plus 6. So y is equal 3. So we get this point. Now, see, kind of like we're filling up the hole. And then when x is equal 2, for example, y equal minus 3 times 2 plus 6, which is 0. So here's 2, 0. And then just graph the line. So you can see it's continuous on its domain. It's also continuous at x equal 1. It's continuous everywhere from negative infinity to infinity. And that's it for this example.